Good morning students. Myself Maheshwari from CSE department. Today I would like to explain the shared pages. In yesterday class I told what is continuous memory allocation and segmentation, fragmentation and paging and the structure of the page table. In that paging we learn some advantages in that are shared paging, hash paging and inverted paging. Those three we learn in this section. So shared pages which is nothing but it is a paging. Another advantage of paging is possible of sharing common code and re-entered code. Paging of the process address can be shared. If the code is re-entered, it never changes during execution. Thus, two or more processes can execute the same code at the same time by using of shared pages. And in this shared code, it is the copy of read and write re-entered code shared among the process. Similarly, it have the multiple threads by using of sharing the same process at the same space, all useful of inter-process communication. If the sharing of read and write pages is allowed and it is have the private code and data, each process keeps a separate code of copy the data. The pages of the private code and data can appear anywhere in the logical address space. See this example here. We learn process 1, process 2 and process 3 is there. See this picture. This is process 1, this one is process 2, this one is process 3. In this process having the data of addition 1, addition 2, process 1, addition 3 and data 1 is there. And the page table of P1 is 3, 4, 6, 1. Okay, and page 2, process 2 having addition 1, addition 2, addition 3 and data 2. Okay, and page table of P2 having 3, 4, 6, 7. Okay, and process 3 having the data of addition 1, addition 2, ED3 and data 3. Okay, and the page table having the data is 3, 4, 6, 2. Okay, see here how physical memory will be mapped here. The data 1 see this picture, this physical memory. Here the three processes are there that are P1, P2 and P3. Check these three processes. The data 1 having the page 1. So the frame page 1 having data 1. Okay, and the data 2 having 7. Okay, so in this 7 place the data 2 will be filled and the data 3 is in 2 page table. So then the 2 having data 3. Okay, you understand? And next this addition 1, addition 2, addition 3 all are having to fill 3, 4, 6. Okay, in 3. See, check here. Process 1 having addition 1, 2, 3 are 3, 4, 6. In process 2 having addition 1, addition 2, addition 3 are 3, 4, 6. And process 3 addition 1, addition 2, addition 3 are in 3, 4, 6. So that the data have in physical memory it will be stored as 3 is addition 1, 4 is addition 2 and 6 is addition 3. So all the data will be filled in this physical memory by using of shared pages. Here what are the pages are shared? So addition 1, addition 2, addition 3 are shared to process in page table of framing of 3, 4, 6. So under purpose the re-entrant code pages of the process address can be shared. If the code is never changes during the execution, thus 2 or more process can execute the same code. Here we can use the same code of process 1, process 2, process 3. Okay, that is the same code is 3, 4, 6. In this physical memory will be mapped. And the structure of the page table. See here, the structure of the page table, it consists of the page can get huge use strength and forwarding methods, and it considered as 32-bit logical space as on modern computers, and the page size of 4 KB is 2 power 12. The page table would have 1 million entries, 2 to the power of 32 by 2 to the power of 12. In each entry, it 4 bits and 4 megabits of physical access space memory of page table alone. That amount of memory used to cost a lot. Don't want to allocate the continuously in memory, and have hierarchical page, hashed page tables and inverted page tables. Here we learn in this structure of the page table, it have hierarchical page table, hash page table and inverted page table. Hierarchical page table. In this, it have break up the logical access space into multiple page tables, and a simple technique, it is a low level page table, and when then paste the page table. Here the two level page table scheme we will be explained here. See this picture. It is outer page table and this one is inner page table, and this is the page table. Okay, in left side it is outer page table, in right side it is inner page table, in middle it is a page table. Okay, see here in this outer page table it will be getting the data to 1 to 500 and 100 to 708 pages, and next one is 929 to 900 page of page tables. This is the indexes, and these indexes again communicate with, it will be split out by using a segmentation of the frames by using like this. So in one it is in one place and it is 500, so it communicate in two level. So each and everything will be communicate in two levels. See here, and here the second page is 100, so it will be mapped, and 708 it will be mapped. So again it is also communicate with two level. Okay, and see here in this page 929 is mapped and 900 is mapped, so it is also done the two level. So this is the structure of two level paging by using of outer and inner of pages of page table. The two level paging example is a logical address on 32-bit machine with 1K page size is divided into a page number and a page offset. The page number consists of 32 bits and the page offset is consist of 10 bits. Since the page table is paged, the page number is further divided into 12 bits per page number and 10 bits per page offset. So this is the logical paging table. See here the 12 bits per page number and 10 bits per offset. If it have the other process of P2, then it will be take the 10. Okay, because on the machine it have 32 bits. Okay, so on the purpose if it have the two pages then it will be divided into page number and page offsets, where P is the index of the outer page table and P2 is the replacement with the page of the inner page table. Here P1 is the outer page table, P2 is the inner page table. So it is known as forward mapped page table. It is known as forward mapped page table. The address of the translation scheme. See here in this picture how it will be address will be translated. See here the logical address is P1, P2 and D. In this P1 it having the 12 bits and P2 having 10 bits and D having 10 bits. D means offset, P1 means outer and P2 is inner page. Okay, see here the P1 of outer page table will be mapped in this page and the P2 of page table is mapped with P2 and then it will be offset will be added. So this is the address of the translation scheme. Next, coming to three-level paging scheme. In this three-level paging scheme, it have outer page, inner page and offset is there. The outer page having and the data size is 42 and inner page is 10 and offset page is 12. Okay. In second outer page is in 42. If the pages are increased, then it will be split up of 10, 10 and offset. See here. This is the 64. And outer page, inner page and offset they have 64. In this 64 it will be split as the outer page is 42 and inner page is 10 and offset is 12. Okay. And if it is a second outer page, then it will be in 32 bits and the outer page is 10 bits and the inner page is 10 and it is the offset of 12. So this is the three-level paging scheme. This is the three-level paging scheme because it have P1, P2 and P3 is there. And hashed page table. In this hashed page table, it is a hashed page table and the virtual page number is into virtual address is hashed into the hash table. There are used to handle address space higher than 32 bits. It is greater than 32 bits and the hash value is virtual page number. The virtual page number is all the bits that are not a part of the page offset. Okay, and the virtual page number is hashed into the page table and each element contains the virtual page number and the value mapped page table and a point to the next element. Here each and every element consists of 3 points, that is the virtual page number and second one is the value of the mapped page frame and third one is a pointer to the next element. In this virtual page number are compared into the chain searching for a match and if the match is found, the responsibility physical frame is extracted and the variation of 64-bit address is clustered page tables and similar to the hashed but each entry refers to the several pages such as 16 rather than 1 and especially useful for space address spaces where memory referred as continuously stretched. So the hash table will be used. So see this picture. See this picture. It is the hash table and it is physical memory. It is the hash function and these two are logical address and physical address. The hash function having the page number and the offset. So the hash function having the hash table, so that will send the data by using of sequence. So in that sequence the physical address will be converted to the physical memory. See here the physical address will be in physical memory. See here the hash function will give the hash table and it have address space of greater than 32 bits and it have the virtual page number and the virtual page number is all bits that are not a part of the page of offset. Here the logical address having the page number and D is offset, and so here the sequence of, let me assume QS and PR will be sent by using of sequence address. So in this R will be stored at physical memory. So on that purpose the R and the offset will be bring out in logical address, so that the so it is in physical address, that physical address will be mapped in physical memory. So this is about the hashed page table. And inverted page table. In this inverted page table, the table is global page table which is maintained by the operating system for all the process. In inverted page table, the number of entries is equal to the number of frames in the main memory. It can be used to overcome the drawbacks of page table. In this inverted page table, it overcome the problems or drawbacks of the page table. For that purpose, inverted page table will be used. So here one entry of each real page of the memory, and then each process have the page table and keep the track of all possible logical pages, and the tracks all physical pages. Entry consists of virtual address of the page stored in the real memory location, and use a hash table to limit the search to one or at most a few page table entries. And TLB can accelerate access. How to implement the shared memory? It have one mapping of virtual address to shared physical address. See this? This is the page table. This is the page table of inverted. So in this inverted page table, it has the CPU, page table and physical memory. So see here, it will be logical address and physical address is there. So the CPU will send PID. PID means page ID, identification, and page number and offset, D for offset. So in this PID is searched in page table of PID. So whatever the PID is referred, that PID is searched, and whatever the data is there, that data is searched. In that, if it have the data of I, presume, so the I will be translate to the physical address, and the data offset will be taken from logical address, logical address and page number of referred page ID. So that will be stored at physical memory. This is the inverted page table. So in previously we know the shared pages we explained, hashed page table explained, inverted page table will learn. But here the new word we can hear, that is PID. PID, which is nothing but process, sorry, page ID, page identification number. It is reference to the page number. Okay. So page number, which is nothing but it is the index of the pages. Dear students, all of our yesterday class and today class about the memory management. In this memory management, we learn in continuous memory allocation. Okay, so in this continuous memory allocation, it allocates in main memory. So if it is continuously allocated, then the problem is occurred. So on that purpose, we can use the fragmentation and segmentation. So in this fragmentation, it have the two characteristics, that is external fragmentation and internal fragmentation. Okay, and segmentation will be used. Each and every segment will play the role of key points. That is, if we execute the complex program, then we can segmented the program as main program, and functions and execution and running. So all are in each and every segment. So on the purpose, the segmentation will be used so as to simplify the complexity. And next, the paging will be used to the drawbacks of external fragmentation, and the paging will be used to storage. And this paging having page structure, and how we defined in this page structure, again we can recollect. This is the page table. In previous class I explained the paging example. See here clearly. Again I repeat if you are not in the understanding. Okay, this is the logical memory. This is the logical memory, this one is physical memory. Okay, here the logical memory is used to 16 bits, that is 0 to 15 bits. See here 0 to 15 bits. So each and every bit will be segmented of 4 bits, that is 0 1 2 3 is first 0 bit, and 4 5 6 is in first page number, and 8 9 to 8 9 10 12 is second, and 12 13 14 15 is third page. Okay, let we assume that. Okay, so in this page table it have the page number and frame numbers, that is the page 0 1 2 3. Okay, 3 is there, and the data having 5 6 1 2 is in page table. Okay, how it will be filled in this physical memory, check it. Okay, in page 0, so it have the 5. In page 0 it have 5. 5 into how many segments is there? 4. So how much it is 5 into 4? 20. Okay, in 20th place the physical memory is filled with page 0. That page 0 is A, B, C, D. Okay, okay, 0 is filled like this. And the page 1 is 6. So 6 into 4. 6 4 shall 24. That 24 place is filled with page 1. Page 1. And page 2 having the 2 having I, J, K, L. Okay, 2 and have 1. So 1 into 1 into 4, that equal to 4. The 4 will be placed at I, J, K, L. Okay, this is the very important example, that's why I told you again. And in page 3 what is the data? 2. So 2 into 4. 2 4s are how much? 8. In the 8th frame it will be placed M N O P. Okay, so this is the example of the page. So how it will be placed with logical memory and physical memory by using the page table. So this is the free frames. Here the frames are empty, then we can call as a free frames. Check here before allegation and after allegation. Before allegation and after allegation. See here picture. Children, this is the new process of page 0, page 1, page 2, page 3. And free frame list is 13, 14, 13, 18, 20. Here we can segment the 4 pages. Okay, in the frame. So the new process having, so in page 0, page 1, page 2, page 3. So it will be filled with page 0 is 14, page 1 is 13, page 2 is 18, page 3 is 20. Okay, so the 13 will be placed at page 1, 14 is placed at page 0, 18 is placed as page 2, and 20 is placed as page 3. This is the associative memory. In this associative memory it is a parallel search. Okay, this is parallel search. In this parallel search it have page number and frame number, those are parallelly searched by using of address translation. So in this address translation, it get frame out and from page table. See here, this is the paging hardware of TLB. Translate lookup buffer. So here we can check the ratio, that is miss ratio and hit ratio is there. The CPU is logical address and physical address is there, and physical memory is there. Logical memory and logical address and physical address is there, and logical memory. See this here. The logical address of page number and D is offset. What I said, D means offset. So the page number will be in TLB, translation lookup buffer. So buffer is a temporary storage, so that storage having the page number and frames is there. Okay, in this page having init, then enable, it is enable, hit, so it will be getting from F. If the page number is not in TLB, then it is miss, then it get the page table check, then after whatever the data is there, that will be framed, and the D is getting from the logical address of data offset. Physical address, so it is stored at physical address. So memory protection will be used as valid and invalid bit. Again I explain, this is very important. See here, there are the 6 page numbers, that is page 0 to page 5. In this page table, here the frame numbers. If the frame numbers having the data means ఇక్కడ కనుక వాల్యూ కనుక ఉంటే అప్పుడు మనం వ్యాలిడ్ బిట్గా రాసుకుంటాం. ఇక్కడ డేటా కనుక లేకపోతే అంటే బిట్ అనేది లేకపోతే అక్కడ ఇన్వాలిడ్ బిట్గా రాసుకుంటాం. అది ఎలా రాసుకుంటాం ఒకసారి చూడండి. ఇక్కడ ఫ్రేమ్ నెంబర్స్ అనేది సీక్వెన్స్కి ఇచ్చాడు. ఫర్ ఎగ్జాంపుల్ ఈ నెంబరింగ్ తీసుకున్నాడు, అది మీరు ఏదైనా తీసుకోవచ్చు యాజ్ యువర్ విష్. ఓకే, సో చూడండి, 0th పేజ్ దగ్గర 2 తీసుకున్నాడు, 1 దగ్గర 3, 2 దగ్గర 4, 3 దగ్గర 7, 4 దగ్గర 8, 5 దగ్గర 9 తీసుకున్నాడు, అండ్ 6 and 7 are 0 తీసుకున్నాడు, అంటే ఎంటీ అనమాట. ఓకే, సో ఇఫ్ ద డేటా ఈజ్ ఇన్ ఫ్రేమ్ నెంబర్ దెన్ ఇట్ ఈస్ వ్యాలిడ్ బిట్ అనమాట. సో వ్యాలిడ్ బిట్ మీన్స్ వీ కెన్ రిప్రజెంట్ ఇట్ యాజ్ వి. డేటా ఈజ్ ఇన్ 2 ఈజ్ ఇన్ పేజ్ 0, దెన్ వి. 3 ఈజ్ ఇన్ పేజ్ 1, దెన్ వి ఫర్ వ్యాలిడ్. అండ్ 4 is in 2, then V. 7 is in 3, then V. 4 is in 8 is in 4, then V. And 9 is in 5, then V. Here you clearly observe in 6 and 7 are 0, then there is no data in frame number, then it is in invalid. Okay, how we map it in physical memory? See here, the 2 having 0th page, okay, and the 3 having first page. చూడండమ్మా, ఈ టేబుల్లో మనం 2 దగ్గర ఏముంది, 0 పేజ్ ఉంది, సో 0 ఫిల్ చేసాం. 3 దగ్గర ఏముంది, ఇది పేజ్ నెంబర్, ఇది ఫ్రేమ్ నెంబర్, చెక్ చేసుకోండి. దిస్ ఈజ్ ద పేజ్ నెంబర్, దిస్ ఈజ్ ఫ్రేమ్ నెంబర్. ఓకే, పేజ్ 4 దగ్గర ఏముంది, పేజ్ 2 ఉంది కాబట్టి పేజ్ 2 ఫిల్ చేసాం. అండ్ పేజ్ 7 దగ్గర ఏముంది, 7 ఫ్రేమ్ దగ్గర ఏముంది, పేజ్ 3 ఉంది. అండ్ 8 దగ్గర ఏముంది, పేజ్ 4 ఉంది. అండ్ 9 దగ్గర ఏముంది, పేజ్ 5 ఉంది. సో అండ్ అప్ టు హౌ మెనీ పేజ్ టేబుల్ హ్యావింగ్ ద పేజ్ నెంబర్, ఫ్రేమ్ నెంబర్స్, దోస్ ఆల్ ఆర్ మ్యాప్డ్ లైక్ దిస్ ఇన్ ఫిజికల్ మెమరీ. This is the shared page example. Presently said shared page, which is nothing but it is the advantage of paging, is possible to share in the common code అండ్ రీ-ఎంటర్డ్ కోడ్. అంటే కొన్నిసార్లు మనం ఒకే కోడ్ని రిపీటెడ్గా రాయాల్సి వస్తూ ఉంటుంది. అలా రాయాల్సి వస్తూ ఉంటే రిపీటెడ్గా రాస్తూ ఉంటే ఏమవుతుంది, మన కాంప్లిసిటీ పెరిగిపోతుంది. అలా కాంప్లిసిటీని తగ్గించడం కోసం వీ కెన్ యూజ్ ద షేర్డ్ పేజ్. సీ దిస్ ఎగ్జాంపుల్ హౌ వీ షేర్ ద పేజెస్. Process 1, process 2, process is there. Process 1, process 2, process 3 is there. In this process, the same data is ED1, ED2, ED3. Okay, see here, the same data is in process 3 is ED1, ED2, ED3, and process 1 is ED1, ED2, ED3, and process 2 is ED1, ED2, ED3. Those three are the same, so we can use the shared pages. We need not to write నెంబర్ ఆఫ్ టైమ్స్. సో పేజ్ 1కి ఒకసారి, ప్రాసెస్ 2కి ఒకసారి, ప్రాసెస్ 3కి ఒకసారి అలా రాసుకుంటే పెరిగితే ఏమవుతుంది, ఫిజికల్ అడ్రస్లో మెమరీ అనేది అంటే ఏమవుతుంది, వాటిగా సరిపోతుంది, కాంప్లెక్సిటీ పెరిగిపోతుంది. అలా కాకుండా మనం కనుక ఉన్నదాన్ని సేమ్గా ఉన్న వాటిని షేర్ చేసుకోగలిగితే, కోడ్స్ అయితే షేర్ చేసుకోగలిగితే మనం కాంప్లెక్సిటీ అనేది తగ్గించుకోగలుగుతాం. సో దానికోసం పేజ్ టేబుల్లో చూడండి ఎలా తగ్గించుకోవాలి మనం అనుకుంటే, చూడండి ఇక్కడ పేజ్ టేబుల్ ఏమి ఇచ్చారు, ది సేమ్ కోడ్ విల్ బి యూజ్డ్ ఫర్ ED1 is 3, in page 2 ED1 is 3, and page 3 ED1 is 3, and in process 1 ED2 is 4, in process 2 ED2 is 4, in process 2 ED2 is 4, same, and in process ED3 is 6, in process P1 ED3 is 6, in process P3 ED3 is 6, the same, all are in same, so we can share the pages. Okay, and see, in page 1 data 1 is 1 and data 3 is process P3 is data 3 is P2 and data 2 is 7. Okay, see here how we filled in physical memory, how it will be filled in physical memory. In data 1 is in one first frame, so data will be mapped, and in second frame of page table it have data 3, so data 3 will be mapped, and in data 2 of process 3 is in 7, so it will be mapped. Okay, and remaining all are used in the same frames, that is 3, 4, 6 of ED1, ED2, ED3 in P1, ED1, ED2, ED3 in P2, ED1, ED2, ED3 in P3, all are used 3, 4, 6 frames. That's why it we used the same data in ED1 for 3, ED2 for 4, ED3 for 6. So those all are used shared pages. Okay students, I hope all of you understand. So it is very important topic, the paging techniques. You must learn, you must put keen observation. So whatever the pictures we given and what are the examples we can given, all you learn, you must to follow it. Thank you students.